In this episode of Calculus Made Easy, we're going to discuss about Taylor and Maclaurin series. Now, you may be wondering what exactly is Taylor and Maclaurin series. Well, Taylor and Maclaurin series are mathematical tools used to represent function as infinite series of polynomial terms. On the other hand, Maclaurin series is a special case of Taylor series where the expansion is centered at x equals to 0. As for the formula, the Taylor series expansion of a function f(x) about a point A is given by Now let's talk about e to the power x. The function e to the power x, where e is a Euler's number, is given by the following formula. This formula represents the Maclaurin series expansion of the exponential function e to the power x. The series is an infinite sum of terms where each term is a power of x divided by the factorial of its component. Here is the graphical representation of e to the power x. Ever wondered how we got e to the power x? Look at the steps below to find out. Now let's use Taylor's series expansion formula to derive the Maclaurin series expansion of e to the x. We have the Taylor series expansion formula, and now for the function e to the x, we'll expand it around a equals to 0 since we are deriving the Maclaurin series. Let's denote the derivatives of e to the x evaluated at a equals to 0 as follows. We know that f to the power 0 equals to 1, and we also know that f prime 0 equals to 1, and f double prime 0 is also 1, and so on. Now, the Taylor series expansion of e to the x about a equals to 0 becomes e to the x equals to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on. This series is an infinite sum of terms where each term is a power of x divided by the factorial of its component, beginning with x to the power 0 divided by 0 factorial, which is also 1. Derivation of sin x using Taylor series. The Taylor series expansion of sin x centered at e equals to 0 is given by. To derive this, we need to find the derivative of sin x at x equals to 0. We know that fx equals to sin x, so f centered at 0 will be 0, and the first derivative of sin x will be cos x, so f prime 0 equals to 1, and the second derivative will be negative sin x, and hence will be 0, and third derivative will be negative cos x, so it will be negative 1, and so on. And using these derivatives, we can write the Maclaurin series of sin x as sin x equals to x minus x to the third power over 3 factorial plus x to the fifth power over 5 factorial minus x to the seventh power over 7 factorial. Similarly, here is the graphical representation of sin x. Derivation of cosine x using Taylor series. The Taylor series expansion of cosine x centered at a equals to 0 is given by, again, we need to find the derivatives of cosine x at x equals to 0. So we know fx equals to cos x, so f centered at 0 equals to 1. And the first derivative of cos x will be negative sine x, so f prime 0 will be 0. And the second derivative will be negative cos x, so it will be negative 1. And the third derivative will be sine x, so likewise it will be 0, and so on. And using these derivatives, we can write the Maclaurin series of cos x as cosine x equals to 1 minus x to the second power over 2 factorial plus x to the fourth power over 4 factorial minus x to the sixth power over 6 factorial. And here are the graphical representations of cosine x. Now this is the graphical representation of sec x. Likewise, this is the graphical representation of tan x. Here are the formulas we derived earlier in the video. Make sure to remember it. Let's take a mini quiz. Do you know which equation is known as the most beautiful equation in mathematics? Take a guess. Drum roll. You got it right. It's Euler's identity. It is called the most beautiful equation in mathematics because it elegantly combines 5 of the most important mathematical constants: e, I, pi, 1, and 0. Euler's formula states e to the power ix equals to cos x plus I sine x. Now let's substitute x with pi into the Euler's formula, and we'll get e to the power I pi equals to cos pi plus I into sine pi. And earlier in the video we derived sine x and cos x using the Taylor series expansion. So now we will substitute all the x values from that formula with pi, and so we will get sine pi equals to 0 and cos pi equals to -1, and so we have e to the power I pi equals to -1 plus I into 0, and hence we'll get -1, and hence Euler's identity emerges, and we're left with the formula e to the power I into pi plus 1 equals to 0. As for the limitations, Taylor and Maclaurin series may not converge for all functions and points. Functions with singularities or discontinuities may pose challenges in convergence. While the Taylor series provides an approximation to e to the power -x2, it requires an infinite number of terms to represent the function exactly.
Okay, oddly enough, I actually understood that.
That's all for today, and keep learning.